The class today, we're going to look at Apache Spark, which is similar in its purpose to Hadoop, but it has certain advantages. It was released after Hadoop, and it has certain advantages that we'll speak about. So in terms of Spark, the most similar framework is Hadoop, and Hadoop was proposed before or was released before Spark. So Hadoop is an implementation of Google's MapReduce framework. And we see that it's been gaining in popularity since around 2010 or so. This is Google Trends, just the number of searches related to Hadoop in red, where we see that there was an increase in popularity and a slight decrease, which coincided with the increase in popularity of Spark. So in some sense, Spark is a competitor to Hadoop. It's a slightly more modern framework. Both are still in use. It's important to understand Hadoop, I feel, before talking about Spark. But Spark has recently become more popular. So this is up to the current day, 2021. So we see that it has surpassed Hadoop in terms of popularity, at least in terms of Google searches. So Spark is becoming a very popular framework, competing with Hadoop. So why do we have this Spark? How does it improve upon Hadoop? What's the main benefits of Spark versus Hadoop? So what is the main weakness of Hadoop? So we'll talk about that in a little while. First of all, we have to recall the data transport costs, and we have to recall the slide from the first class where we spoke about overall the amount of data we can transfer from different types of storage to CPU, the rates at which we can transfer data, and the latency in terms of how long it takes to get back data after making a request. And we spoke about how main memory is much more efficient, both in terms of throughput and access latency, than the disk, right? So if we could do processing or use more memory, main memory, the RAM of machines, that would be beneficial. So that's one of the aspects in which Spark is different. Of course, it's not just throughput and access, but based on this latency here, if we do lots of random accesses on the disk, it can really slow down a process, which is why we always try to do sequential reads and writes to the disk using sorts and so forth. So we've spoken about that before, which can be more efficient in main memory. So in general, if we can try to exploit more main memory, that might be beneficial for the run times of our tasks, if we have the main memory available, of course. So if we look at the MapReduce Hadoop framework, essentially we've seen this process of starting with an input where we have some lines. This is doing a word count. We parse the words at a 1. So the keys will be the words values 1, and then we split the data up across different machines. So we do a partitioning, and we sort batches of partitioned data. And then we write this to the disk. So where I use these dashed lines here, it means that this is data that we're streaming or that are in memory. And then when it's solid line, it's something that's written to the disk. So we have our input in the disk. We create the first sort of partitions of data that we're going to shuffle. We write them to the disk. Then on the other side, we have to write it to the disk on the other side. We need to write these chunks of sorted data on the machine that will receive the data. And then we can merge sort these, which creates an iterator in memory, which we can then essentially group the values by a given key. And then we write our output to the disk again. So what's happening here is we have a read from the disks of the machines for the input. We have a write here before the data are shuffled across the network. We have another read here and a write. So we need to read this data to transfer it over the network so that we can write it on the other side. And then we have a read here again, where we need to read these data again. And then we have our final write here on the output. So we see that we have quite a lot of disk activity here. And oftentimes Hadoop clusters or Hadoop jobs can be limited by the disk, in the sense that the hard disks of the machines can be a limiting factor in terms of the amount of parallelism that they allow. So, okay. So here, again, these dash things, the symbol I use for RAM, for main memory. So it means that these data here are stored in main memory. Okay. So the benefit of using the disk, of course, is that we don't have any strict, strong requirements for memory. Essentially, all of the steps here, we're just streaming data in memory. We're not storing large amounts of data in memory. Here, I guess you could say we are storing large amounts of data in memory to do the sort, but they are fixed size batches. So we'll have a certain number of key value pairs in each batch that we store in memory. And when we fill up a batch, we'll write that to the file and then start a new batch. Okay. So MapReduce always coordinates between phases and between high-level tasks using the hard disk, so high-level jobs. So it uses the hard disk a lot, effectively, is the message. So we see that essentially within a typical MapReduce job, we'll have 3 reads and writes, and then we'll, whether or not this is added to it, but we will have stored the data on the disk in HDFS, and then we'll have 3 reads and writes. So in general, yeah, we would expect 3 reads and writes per job, per MapReduce job in Hadoop. Okay. So we saw this cost of using the disk already, counting words, even in the first lab, where when we counted words in memory, it took seconds, right? It was mainly the cost of reading the file. But if we did it on disk using sorts and so forth, and using the second process that you use for n-grams using the disk, it would take minutes. In this case, for a certain value of n-grams, it wasn't possible in memory anymore, so that was reasonably acceptable. Better it takes minutes than not be possible at all. And over MapReduce, we have this added overhead as well of the network. Of course, at some stage, we can't process the disk of one machine is not going to be sufficient, and it would be faster to parallelize certain aspects. And in that case, MapReduce would be better, but it would still take minutes to considering the disk activity, the use of the network, and so forth. So any alternatives to these options? So we have in memory on one machine, on disk on one machine, and on disk on multiple machines. Big hint. Any ideas what we could think about as an alternative? Yeah, so we could use RAM, main memory on multiple machines. And that way we overcome a main limitation of memory, in the sense that, okay, memory is kind of limited on one machine. It can be expensive to get large capacities of memory on one machine. But if we have memory across multiple machines, then we can scale the capacity of memory across multiple machines in a similar way to what we're doing with the disk, right? So rather than having to somehow organize one machine with some massive amount of memory, which in any case, you would still need different CPUs to be able to handle, we can have lots of machines with their main memory pooled together. So yes, in memory on multiple machines, this is the option that we have not really explored. So, okay, in an ideal case, right, we even spoke about this early in the course, that one option would be to try to count words, for example, in memory. Obviously, we'll be able to fit 3 words in memory in this case, but this is a small example. If we scale this up by 1 million or 1 billion, the process would be similar, right? But in this case, we're storing here in memory. We're doing the count in main memory using a dictionary or a map like we saw in the first class. And if we can do that, then we can count the words, and then we can somehow do a reduce where we just sum all the counts, right? And here we again would assume that we can fit all of the words, all of the counts in main memory on one machine. So this is obviously the problematic aspect here, in the sense that if we wanted to have to reduce everything to one machine, for example, then all of the data would have to fit in memory. If it does fit in memory, this would be a lot faster than what we do in MapReduce, right? So what we have here is we have one read for the input, and we have one write for the output to the disk. Okay. And this is not even really necessary. I mean, we could just store the data here in memory and work with the data in memory here if we wanted. Okay. So here again, we have these dashed lines mean that these are data structures that we're storing in memory. So this is roughly speaking the idea of Spark. It's to try to be able to, where possible, use the main memory of the machines to be able to speed up processes. And ideally, maybe the task can run entirely within main memory on each machine. Okay. If not, there's some workarounds. So essentially the short answer is that Spark, in case the data don't fit in memory, in main memory, in case we don't have enough main memory, Spark can spill over onto the disk. So there are various options on how to store the data, but one option is to use main memory while available. And if it grows too large, then to use the disk. So we'll return to that. We'll see that a little bit later. So Apache Spark, the idea is to program with the main memory. So as opposed to Hadoop, where we're kind of coordinating each phase of each job on the disk, in Spark, we have the option of using main memory or disk or both, using main memory principally and then falling back to disk if it's too large. So the idea of having data in memory as well allows for doing new kinds of applications or tasks that are not so easy to do in MapReduce. Well, they're doable, but again, given that you have to coordinate on the disk all the time, it can be quite expensive to do such tasks. For example, an example of a recursive program might be something like a breadth first search or a depth first search in a graph. We'll also see examples later like PageRank, where essentially you need to apply iterations. And you don't know how many iterations, you're just applying an iteration over and over and over again until some termination criteria is reached. And the benefit of Spark for that is that if you have the data in memory, you don't have all of this coordination. You can get the data in memory and then do these sorts of recursive tasks on it. So this is quite useful. So this is the principal difference that Spark really tries to leverage the main memory of the machines. So the storage shifts from this concept of HDFS, Hadoop Distributed File System, which is purely based on the disk, to a more abstract notion in the case of Spark, which is an RDD, which is called the Resilient Distributed Data Set, which abstracts at an even higher level the details of how the data are actually physically stored. So like HDFS RDD, the RDDs abstract the distribution, the fault tolerance, etc. But RDDs can also abstract the hard disk, the main memory. It can even abstract the system used for storage. So you can have RDDs that will read directly from HDFS, from different types of distributed file systems, from NoSQL stores that we'll talk about later in the course. So these RDDs provide a very high level abstraction, even more high level than HDFS. So somehow the data in an RDD can be stored in many different ways. So so this would be the idea of Spark again, where we have here essentially an RDD. So this here would be considered to be an RDD, which is somehow a data structure that's stored on multiple machines, possibly in memory, possibly on disk. And this here again would be an RDD. Okay. So if the unique words don't fit in memory, again, what can happen? The RDDs can fall back to disk depending on the configuration of the RDD. So what does RDD mean? Resilient distributed data set. Resilient means it's fault tolerant. So a failure in the machines should not negatively affect access. You should still be able to access and process the data. Distributed means partitioned over multiple machines. And data set is a set of data. So RDD is a central notion in Spark. Any questions or comments? Okay. So RDDs can have multiple virtual partitions on one machine. Just to clarify this, because the other example, I had one partition on each machine, but RDDs contain partitions, and partitions, we can have multiple, we can have 0 or many partitions on a particular machine. Just to say that it's not a one-to-one correspondence between partitions and machines. There are different types of...
I have a question. Sorry.
Sure, go for it.
Could you go to the previous slide, please? Why would you want to have more than one multiple virtual partition on one machine? Doesn't it have a big overhead?
So there are special functions that allow you to process data by partitions. What can happen is sometimes, for example, you can reduce the number of machines. You want to separate certain types of data into certain partitions, which is not so common. So there are use cases where you would like to, you might end up having more partitions than machines, but a typical scenario would be indeed that you would have one partition per machine. So there are things in Spark that allow you to process per partition. There are things that allow you to reduce the number of partitions, to manage that somehow manually. So it's not necessarily the case that there's one partition per machine. But you're right, that probably the common case would be to have one partition per machine.
Okay, thank you.
Okay, nice. So we'll see some of the features that work per partition later. So in terms of RDDs, we have different types. So we have, like I mentioned, we can read data from lots of different locations. We have like a Hadoop RDD, filtered RDD, mapped RDD, shuffled RDD, union RDD, Python RDD, JSON RDD, JDBC RDD. This is a Java database connector. This is a way to interface with relational databases, for example. Vertex DDD, Edge RDD, these two for processing graphs. We have geographical RDDs, Cassandra, which is an NoSQL database RDD. So we have lots of different RDDs. And in general, Spark, unlike Hadoop, which is a very sort of minimal framework, Spark goes in the opposite direction. Spark provides libraries for doing lots of things. So we have different types of RDDs. We have different types of functions. We have not just map and reduce, but we have all these other functions that we can use. So it won't be possible to talk about everything that's in Spark. Even just focusing on Spark Core, there's so many things that it wouldn't be possible to present everything, nor would it make sense. But one thing that is a key notion here, okay, so all of these different specific types of RDDs permit specific operations and can be read from different types of inputs. But a very important type of RDD here is the pair RDD. And why is that? It's because it facilitates or provides the ability, pair RDDs have interfaces for running MapReduce. This is MapReduce here, style operators. So in MapReduce, you always work with keys and values, and a pair RDD also contains a set of, or a bag, or a list, a sequence of key value pairs. So essentially, this RDD is of central importance for many processing tasks. So we can dive into an example. We'll use a similar example to what we saw before for Pig, where we have customers, items, times, and prices. And what we would like to do is to count how many number of customers buying each premium item per hour of the day. Okay. So we want to count the customers, how many customers buy, for example, Nescafe at between 3 and 4 p.m. Okay. So to simplify the data, we're going to write it like this, where this is a customer 1, customer 2, customer 3, customer 4, item 1, 2, 3, 4, the hour. We'll just assume it's been extracted for simplicity, and the price is a number. So we'll simplify the data like this, and then we'll jump into an example, right? So we're still targeting the same question. So here's our data, and we assume we have a massive file. It could be gigabytes, terabytes, whatever in size, and it's stored on HDFS on our disk. So the first thing we'll do in Spark is load. So we're going to load the data into an RDD. And this doesn't necessarily mean that we're going to load all of the data immediately into memory. It could be, that could be the case, or it might not. So we'll talk a little bit later about this, but essentially for the moment, conceptually, we're doing a load. It doesn't actually load the data right now, but we'll return to this. So we've loaded the data as an RDD, and we can start to apply processes on the RDD. So the first thing we can do is we want to filter to only consider premium items. So we're going to apply a filter such that price is greater than 1,000. Okay, price being the last column here. We assume the fourth column. So we get all of the items left that have prices greater than 1,000, and we have a blank partition here. Okay, so this blank partition occurs because we filtered all the data that were in that partition before. We can call a method called coalesce, which in general isn't so commonly needed in practice, but it allows you to set a new number of partitions. Okay, so you could here, for example, coalesce and pass the number of machines you have. So what will this do? This will just essentially reduce the number of partitions to have 3. So why would we want to call that? Maybe we have a very large data set and we filter a lot of it, and then essentially we end up with empty partitions or only a small fraction. Maybe we want to coalesce all of the data onto one machine. So coalesce says, okay, please reduce the number of partitions to at most 3. Okay, and we have to continue. Slide is not long enough. So we continue on the other side. After coalesce, what we're going to do is apply a distinct. Okay, and we see a gap here. So we want to remove all the duplicate items in the partitions. Okay, so this requires shuffle because we may need to know about duplicates that exist across different machines. In this case, let me go back. It seems that the data were already pre-partitioned by customers. So in this case, it's not so necessary, but the distinct in the general case could require a shuffle. This is what the shuffle means. It means that you can't apply a distinct locally on each partition, on each machine, but rather you may need to coordinate or send data to make sure that you have the same tuples will appear on the same machine. So next we can apply a map, and a map requires a definition of a key and a value. So the key in this phase will be the item and the hour. That would be, for example, I2 and 08, and we're going to add a 1, right? So the 1 is essentially, as we've seen before, we're going to use that for counting. So we're going to just sum the ones. So once the data have been mapped in this way, then we can call, for example, count by key, which will essentially group the data for us by key, and then producing a 1 for each key. It will then sum or count the number of keys with that value. So I have a different format here for count by key, which is a little bit strange. So I'll have to talk about why this is a different format, what's the difference between this thing and map and the other functions we've seen before. There are details here of these functions as well that I will explain in more detail, but the last part would be then to save, for example, the data. Again, here the dashed lines mean in memory, for example, so we want to save it to the hard disk on HDFS. So there are details of what each of these functions do, right? So what I wanted to do is give an example, a high-level kind of example to give an idea of what a process would look like in Spark. So we see that instead of having these very fixed operations like map and reduce, we have more low level or high level. I'm not sure which, but we can call things like filter. We can call things like distinct or map or count by key. We can count these higher level functions. So it's maybe somehow at the moment a cross between something like pig and MapReduce. Okay, so I'll get into the details on what these different functions do and what's the difference, for example, why these things have different formatting and so on. But any questions or doubts for the moment? Okay. So transformations in action. So the first thing I'm going to explain is why I had these two things in different formats. Why these two things here are indicated with different formats. So the short answer is that one is a transformation and the other is an action. And it's an important distinction in Spark. So what is a transformation? What is an action? So transformations, the things I was doing with purple font and dashed lines, are run lazily. They're not actually executed straight away because you don't actually transformations. The result is not really needed immediately. So it's a similar concept as to what we saw in Pig, where it doesn't immediately run anything until you really need the output. Okay, so that way, what it hopes to do is to be able to gather multiple operations into one kind of process, let's say. So transformations are run lazily and they result in virtual RDDs. So they're only run to complete an action. So what does it mean, a virtual RDD? It's just a conceptual logical RDD. It's not a physical RDD. It doesn't actually exist yet, okay? It's like an interface over the result of a transformation. So transformations are only run to complete an action. For example, if we have this thing here, and these are all these transformations. So we load, filter, coalesce. These are not run. They're not actually executed, okay? Not until we run an action. So what are the transformations? So in general, we have there's a long list of transformations available in Spark. According to the documentation, these are the most commonly used ones in practice. Some of them will have familiar names and some will seem a little bit strange. So we'll go into details brief details on each of them. First of all, any guesses why I've underlined some here and not others? So the reason why some are underlined is because they require a shuffle. They require coordination across different machines, typically because they require more than one tuple. What else can we describe here? There are a couple of things to mention. We have OR here is an RDD. So typically we'll be calling these transformations on a given RDD. So each shuffle needs coordination between machines. So typically, yes, not in every case, it might be possible if the Spark framework were clever enough. I'm not sure if it would be, but it could infer that a shuffle is not necessary in some of these operations. It could infer that the data are already partitioned correctly. But in general, in the general case, these would require somehow shuffling data or sending data over the network between machines. So what we have is OR, which is an RDD. S here is an RDD, but Spark makes use a lot of the functional programming paradigm where we pass functions as arguments. So these F here are essentially functions that we will pass as arguments. In other cases, we see ... These are usually just like scalar inputs or number strings, booleans that configure somehow the transformation. Yep. So why are some underlined? They require a shuffle. They require coordinating machine data across machines. So we'll take a break. I think it's 3 o'clock. We'll take a break until 3:10, and then I'll briefly get into giving a brief description of each of the transformations listed, of the most common ones at least. Okay. Stop share. Stop recording. Okay. So we'll get into details. Sorry, actually, I skipped ahead. So we'll get into some details on what precisely are the transformations we see here. So the first set of transformations we have are as follows. So we have map, flat map, filter, map partitions with index and sample. So with map, what we do is we take every tuple, every element from OR, we transfer to one output value. So for example, we could map A, B, C to a C, for example, to do a projection. Flat map is a bit different in that we can map an element from OR to 0 or more output values. So for example, we could take A, B, C, and we could produce a set of values, A, B, and AC. So we could add 2 tuples to the output for a given tuple, or 0 outputs. An example would be maybe, for example, we have a string and we parse out a set of words from the string. So that would be flat map 0 to 1, 0 or more output values. Filter, we can apply a filter in an RDD, which will return all of the elements of OR that satisfy F. So for example, we filter such that A is greater than B. Map partitions. So this is similar to map, but the input is rather a partition of an RDD, which we could see as an RDD. Okay, it's a list of tuples of elements. So it maps all of the elements to the output. It maps all elements of OR to the output, calling the function once per partition. So in this case, the function accepts a partition of the RDD. And then, for example, we could define that we want to project A and C from each partition. So this operates at the level of partitions rather than at the level of individual tuples within partitions. We can also do a map partitions with index, where F takes an additional argument that provides the index of the partition. So for example, we could project the index of the partition along with the A and C columns from the RDD. Admittedly, these two functions here I haven't seen used much in practice, particularly this one. And I struggle to think of a use case where you would want to know the index of the partition. But in any case, you can maybe use this to manually manage certain partitions. Much more common to use the first three. So sample. So we can take a sample from an RDD, and the arguments are W, F, and S, where W is a Boolean to indicate with or without replacement. F is a fraction. So say I want to sample 10%. Okay, so we would pass 0.1. And S is a random seed used for the sampling. In case we wanted to replay a sampling that we used earlier, we could use the same seed each time. So with replacement, what does with replacement mean? If we have, for example, 3 letters A, B, C, and we sample 2 elements from it. So if we sample with replacement, let's say in the first sample, we take C. Okay. So with replacement, if that's true, then we should add C back to the set before we sample again. So a valid response would be C, C, if we were to sample 2 elements. Without replacement, it means that we would expect the element not to be replaced. So we would have C and then B. So CC would not be a valid output without replacement. Okay. So we have some kind of standard set operations. We have union, we have intersection, and we have distinct. So union does not require a shuffle because we can just take whatever partitions were in both RDDs and we can just add them virtually to the new RDD, right? In place, we don't need to move data for that. For intersection, we do, right? So we somehow need to make sure that we have the same tuples from OR and S on the same machine and the same partition to be able to do this. And distinct removes duplicates. Okay, so it will remove duplicates. It will turn it into, I don't want to say it turns into a set because it's always a sequence of tuples, but it will remove the duplicate tuples from the RDD. Okay, perhaps the most important ones in terms of if we think about, for example, MapReduce, the MapReduce framework are those that require a pair RDD, that require or assume that the RDD has maps and has keys and values. Pairs of key value pairs. The RDD contains a sequence of key value pairs. So in this case, group by key, we can use this to just group the values by key. So we'll have a key, and then we'll have, like we saw in Pig, a bag of values for that key. Another option would be to do reduce by key. And in this case, we pass a function f. And what we're going to do is we're going to group the values by key, and we're going to use f as a function, as a combiner and a reducer in the exact same sense we mean in MapReduce, to combine and reduce values with the same key. So for example, here we'll take a key that has two values, A and B, and we'll output the key with A plus B. So we'll sum the values for a given key. So this will be used both to combine values, which is used on the sort of map part, and then to reduce values as well later in the very same sense as in MapReduce. I will return to this a little bit later to explain this in more detail. So I know it probably requires more explanation. The same with aggregate by key. So what happens if we want to do something like in MapReduce, but where the same function, we can't apply the same function as our combiner and as our reducer? In that case, we can use aggregate by key, which essentially allows us to do something similar like a MapReduce phase, but we have to define three elements. The first is to define C, which is an initial value. Okay, so an initial value could be a 0, it could be an empty string, whatever it may be. It could also be a tuple of values. We define a separate function for combining and a separate function for reducing. Okay, so for example, for reduce by key, we can use sum. We can define a function which is a sum, and because this is this operation is commutative, associative, and so forth, we can sort of sum things in pairs and then sum all of the results and we'll still get the same value. But if we wanted to do an average, it wouldn't be possible to use reduce by key. If we wanted to do an average, we would have to probably think about using aggregate by key. So we'll return to that later with an example. We can also sort by key. So we can sort our RDD such that it'll be ordered by key, and we have the option of optionally, we can say whether we want it in ascending or descending order, with ascending being the optional, this here means optional, with ascending being the default value. We can apply joins, which will join OR and S, where the condition will be an equi-join by key, which means that we'll join on OR and S such that the keys are equal. We can also use left outer join, right outer join, and full outer join. So we have options in terms of, using these outer joins as well, which we saw, maybe spoiler alert, but we saw was useful in lab 4 when using PIG. We can also do co-group like we saw in PIG, which is group values by key and OR and S together. So it's sort of like doing a union and then doing group by key. So we could apply it in that way as well. Okay, so I know there might be some details of reduce by key and aggregate by key that are not super clear, but I hope you understand the other group by key as well. I'll explain in more detail. Sort by key, join, and co-group I hope are more clear. So other transformations, maybe less common ones, Cartesian product. We can produce every possible combination of tuples from OR and S. So if we have 10 elements in S and 5 elements in, 10 elements in OR and 5 elements in S, we'll have 50 elements in our output. That just depends every possible tuple in S to OR. Same as the Cartesian product in the relational algebra, for example. So we have pipe. And pipe is essentially allows us to interact with our local machine. We can kind of pull data, or we can use the command line of each machine to be able to process data. So we could pipe data into a command on the command line like grep or awk or perl or whatever Python script or Perl script we have, or whatever essentially whatever command line command we would like to process the RDD with. So this is not commonly used, but we can do that if we like. Coalesce we saw, which allows us to merge various partitions into at most n partitions. N might here be the 1, for example, if we just want to work on one machine. It might be the number of machines we have available. It's not so typical to use this, but we have that option. And repartition. Repartition is, rather than merging partitions, it just repartitions all of the data again to rebalance them, creating at most n partitions. So the difference between coalesce and repartition is that coalesce will typically involve merging existing partitions into larger partitions, whereas repartition could break up existing partitions, essentially defining completely new partitions. Okay, and here being again the number of partitions in the output. So any questions? So I will explain these three. These three are key. These three operations I think are very important to understand, and we'll go into them in more detail. So if there's no questions, we'll move on to actions. And actions are where things execute. So essentially what that means is here we're not going to actually do anything, right? So Spark is going to be lazy and not apply transformations. But when we apply an action, they result in a materialized RDD, and all ancestor transformations are run. So for example, if we try to save here, then okay, we need to materialize, we need to create some output, right? So in that case, we're going to apply all of the other transformations up to this point. So all steps will now be run. Intermediate RDDs are not kept. So these are somehow processed and materialized, but it could be the case, for example, that we will combine several filters into one filter with AND, right? So these RDDs, these intermediate RDDs don't really exist. And unless you specifically ask, they won't be stored. So if you were to take this RDD and save it again or do something else with it, then all of this would have to be processed again, right? So we'll talk about that a little bit later. In terms of the actions, we have a list of the most common ones here. You can see the full list in the documentation, which I'll speak briefly about these actions. So we have reduce, which is essentially not reduce by key. We saw reduce by key earlier, but reduce doesn't reduce by key. It reduces all of the data to one value. So it's like in SQL, if you do count. If you do count with group by, then you'll get a count for every group by key. But if you just do count, it will just count all of the things in the table, right? Not by key. So in a similar sense, this reduce will produce one output for the RDD, which will be, for example, a count of all of whatever, right? Whatever we want. Or in this case, we can define whatever function we want. We can just sum all of the values in the RDD and produce one total sum for the entire RDD. So given that this is just one output that we can then read or view, this produces an external value. Yeah. So we can collect, so we can load an RDD into an array into the local application. So if we're working in Python or in Java or Scala or whatever we prefer, we can launch our thing on Spark, and then we can use or.collect, which will load our data into a local array. So this would be typically if we process lots and lots of data and the output's quite small and we want to continue working with it in our application, we can use or.collect. Maybe a top 10, for example, you just want to take the top 100 results or some sample. Or.count just simply counts the elements of or. Again, it just produces a simple value. First, we'll take the first tuple of or. So take will load, essentially, it's like limit. It will load an array of n values from or into the local application. Or you can take sample, right? So it takes the same arguments as before to take a sample of an RDD into the local application. So what all of these have in common is that they produce an output, a value that's not an RDD, but it's a simple number, or it's an array in an application, or whatever. So this requires the results to be computed. Was there a question? Any questions or doubts? Okay.
Yeah, about the function collect.
Yep.
If you use, for example, collect in Python or Java, you would have an array then.
Yep.
And you could operate with it just like in your programming language.
Exactly. Yeah. So you can kind of run something on Spark, and then you can load it into an array, or it might also be an array list. It depends on the programming language, but you can load it into a local data structure and then use that as if it will be loaded into memory in your program. So you'll be able to
Oh, fine.
to continue.
Thank you.
Yeah. Yep. So we have some options for saving. So rather than reading the data into an application, or we can also save the data to a file, which is maybe a more common kind of paradigm for Spark. So you can save it as a text file. You can save it as a sequence file, which we spoke about briefly in Hadoop. Sequence file is like a compressed binary format that's good if you know that what you're going to do with the data afterwards is process it again in maybe Hadoop or in Spark. Or you could save it as an object file, which uses a native Java serialization. So Spark is implemented in Scala with kind of Java JVM environment. So in general, the idea would be the most common would be to save as a text file so that you can read it afterwards in whatever application you want. But you could also, if you want to optimize, save it as a sequence file, perhaps. Or as an object file if you have a complex class structure and you want to remember the exact types of everything. So you can just reload the entire state again without having to parse it from a text file. Count by key will essentially tell you how many values there is for each key. And this is only available for a pair RDD. I'm honestly not 100% sure why count by key is an action rather than a transformation. I've never really gotten a clear answer to that. For some reason, to me, it appears just like a transformation, but in any case, it's an action. They probably have their reasons. So for each then allows you for every element of or every tuple to typically to run some function, which can typically mean to interact with something external, for example, for every tuple in or print to the standard out, for example, the tuple, something like that. Again, not used all that much, I would say, but obviously save as text file is important, and count by key is used a lot as well. Okay. So the key thing with these actions, again, is that once you call the action, it will compute the RDD and materialize the result, including if it depends on transformations, it will call all the transformations that it depends on. So what I'd like to do then is to talk a bit more about these three transformations, which are important as they allow you to do sort of map reduce style operations in Spark. So let's get into a little bit more detail with some examples. So how are the above different, and when would we use the different ones in which sort of scenarios? Okay, so the first case we'll look at is how would we sum all values for each key in OR? So, you know, we have our products and we have a list of ones, and what we'd like to do is just, or, you know, they might be ones, they might be twos, they might be threes, but we'd like to, for each product, sum all of the values in the RDD for each key representing a product. So one way to do this is to do group by key. So what group by key will do is it will take every key, for example, every product, and it will gather together all of the values. Okay, that's what this will do here. So you'll have a key and then you'll have a bag of values. Okay, so that's all it does. It does not apply any aggregation. It just applies the raw grouping. So if you want to later then, for example, apply a sum or something else, you can use map. So we use map because the input output is one-to-one. For every input key set of values pair will output the key and the sum of all those values, right? So we group by key first, which for each key gathers all the values, and then the map will map each of these to the key for the sum of all those values. Okay. So this is not a typical way to do this, right? This is possible, but it's not a typical way in which you would do this sum. So the second option is to use reduce by key, where we just say how to combine values. So what we say is, given a pair of values for a key, what we want to do is sum them, okay? And essentially it will just sum all of the values in the keys, and then we'll sum the sums until there's a final total for all of the sums. So this seems to be a relatively straightforward option. Another option is an aggregate by key, where we have to give an initial value 0, and then we start adding all of the values together. So for a given key, when we encounter the first value in a partition, we'll add 0 to that value. Okay, so let's say the first value we see is 3. We'll take 0, which is the initial value, plus 3. 0 plus 3 equals 3. let's say the next value is 5. So it'll be 3, 5, maps to 3 plus 5, 8. Okay. And then later, maybe we have 8 as the result of that partition, and maybe there's another partition that has 15. So this tells us how to combine the values across partitions, but it's the same thing, right? So if we have 8 coming from one partition and 15 coming from another partition, then we'll sum those again and get 23. So in this case, the combiner and the reducer are the exact same, right? So what are the benefits? So one does not use a combiner. It groups everything. It produces all of the values, okay, for each key, and then it applies a sum. The good news about 2 and 3 is that rather than gathering all of the values, it's rather accumulating a sum of values as it finds new values, as it finds additional values for a key, right? So this means that we never have to have all of the values for a key, somehow process them or generate them. So these are beneficial because they can reduce the data. So in this case, 2 and 3 are doing exactly the same thing. Why is that? It's because the combiner and the reducer here are the same. So given that the combiner and the reducer here are the same, we don't actually need aggregate by key. We can just use reduce by key and pass the function. So in this case, 2 is best, right? So in this case, it's the most concise. It will be the most efficient of the 3 because, well, it will be equally as efficient as aggregate by key, maybe slightly more efficient because it uses a combiner. So reduce by key is a great way to sum all of the values, for example, for a given key. So why would we ever need 3 then? There are certain operations that we might like to do that where the combiner and the reducer won't be the same. So if we wanted to take the average of all values for each key in OR, as mentioned before, in the case of MapReduce, we can't just take averages of averages, right? Because we'll get a different value. So we can't average like all of the values per partition and then average the result from each partition. That will give a completely different result to collecting all the values and then doing the average. So there are three options. One is to apply group by key again, where we essentially group all of the values for a given key. And then in the map, this time we convert a key and a set of values, this time to a key and the average of all those values, which is perfectly fine. Maybe not a very typical way to do it, but we could do that. A way of using reduce by key, we can't use reduce by key alone, but what we can do is we can use reduce by key to get a sum. We can use count by key to get the number of elements, and then we can join the count and the sum, and then in that result, we can divide the sum by the count. Okay, so we get the sum, we get the count, we join the two, which gives us for each key the sum and the count, and then we map it to key sum divided by count to get the average. Okay, so we see that using reduce by key directly is not possible. The third option is to do this here, where what we're going to do is use aggregate by key, where we use a pair. So we use a pair of a sum and a count. Okay. So we need to define two functions here. One is a combiner and the other is a reducer. So the combiner will accept a pair of sum count, a value for the key, and then it will output the sum plus the value and count plus 1. So we maintain, given a new value, we update the sum and the count accordingly. So in every partition, we'll produce a pair, which is a sum and a count. And then for the reducer, we have to reduce all of the values from all of the partitions, and partitions are producing pairs. So in this case, we have to combine two pairs, two sums and two counts, sum count ones, sum count two. So how do we do that? We just sum the sums and sum the counts. Okay. So in the final output of the aggregate by key, what we'll have is a key and we'll have a sum and a count like this here. So what we need then is a final map to be able to divide the sum by the count to produce the final output. Okay. So I'll go through this again in a little bit more detail in case it's not super clear. Maybe you have a rough idea of what it's doing, but we'll go through the concrete example. So 3 here has a combiner, which is great. and it only needs one shuffle. So the big difference between 3 and 1 is that 3 has a combiner. So it's not going to gather all of the values. Rather, it's going to maintain a sum and a count as it encounters new values. It uses it to update one count and one sum for that key, right? So we don't have to gather all the values. With respect to 2, we see that 2 has to do a join, which requires a shuffle. So 3 does not require this join, which is nice. We get to avoid this step here. So we don't have the same cost. We don't have the cost of doing a join here. Why? Because we managed to maintain one value for each key, which is a tuple of a sum and a count. Rather than independently computing the count and the sum and then joining them, we maintain a value which is a sum and a count for each key. Okay, so maybe this is still kind of like what's going on here. It might not be clear, so we'll dive into that. I hope that the first and the second part here is more or less clear. So again, here we first group everything by key, and then we apply a manual function to do the average. Here we do get the sums of all values, we get the counts, sum of all values for each key, we get the counts of each key, and then we join the count and the sum, and then we divide the sum by the count. Here we tried to do everything essentially we could think in one MapReduce step. Okay, so 3 is best in this case. So let's have a look at how 3 is working specifically. So we'll just take some data that are partitioned. This is a pair RDD. We have keys which are products, and we have values which are, I'm not sure, number of customers, for example, who have bought that product. So what we'd like to do is sum the values for each product, for P1, for P2, for P3. So we've defined our function as we saw before, aggregate by key here, and we assume this is OR. So how this works is, first of all, it will start to read the data. So it's not necessarily that it will group all of the data like this, but essentially we can just for the moment assume that that's the case. So for P1, we'll have the value 30, P2, 25, and 30. So we have somehow, we can read the values for each key get an iterator over the list of values with that key. So what we can do then is we can apply this first function here, okay? So it starts with the SC. So the first value we have for P1 is 30, okay? So what it will do is it will take SC, and since we have no SC, we have no sum or count at the moment, we take the 0 value, which is 0, 0 here. So we'll take 0, 0, and 30, okay? And then we'll add 30 to 0, which will give us a sum of 30. And we'll add 1 to 0, which will give us 1. So our new pair here will be 30 and 1, and that's all the values. In this case, we'll have 25 and 30. So we'll add 25 to 0, will give us 25, and 0 to 1, 1. So initially we'll have 25, 1, and then we'll add 30 and 1 to that, give us 55, 2. And we do this for all of these pairs here. And then we shuffle to make sure that we combine for each key all of the pairs, sum the count pairs, and get them onto the same machine. So P1 and P3 end up on the blue machine, P2 on the green machine here. So here we have a list of pairs, and now we need to combine the pairs. So we return to the, okay, so the output then eventually will be this aggregate by key here. So to compute the final output, we'll use the second function here. This is the reducer. So what the second function will do is it will tell you how to combine pairs. So we take 30 and 1 and 10 and 1. So 30 and 1, 10 and 1, and then we sum the counts, 30 and 10 or 40, and 1 and 1 is 2. Okay, and then we take 40 and 2 and 20 and 2, and it will produce 60 and 4. So this is the overall aggregate by key. This is what's going on in the middle, and the 0 count and the combiner are used here before the shuffle, very similar to in MapReduce, the combiner. And then the reducer tells you how to combine somehow, or how to reduce all of the values from the different partitions. So finally, we can do the map, and the map will just divide the sum by the count. So to dig into it a little bit more, if we take this first function here again, we have P130 So how is this result computed? So what we have is a combiner which uses the 0 value and uses this function here. So when we take 30, we start with the 0, 0 value, okay, and then we add 30 to 0 and we add 1 to 0, or 1 to the count. So we get 30 and 1. If we take two values here, we first combine 25 into the 0 value, which will give us 25 and 1. And then we'll take 25 and 1 and we'll introduce 30, which will give us 55 and 2. And so we continue on in this way. So for the second part here, how does this work? So we have a reducer function which takes sum 1, count 1, sum 2, count 2, produces the sum of the sums and the sums of the counts. So given 31, 10, 1, 22, what we'll do is take the 0 value, 0, 0. We'll take 30 and 1, and we'll produce 30 and 1. We'll take 30 and 1, and then we'll add in 10 and 1, which will give us 40 and 2. 40 and 2, we'll add in 20 and 2, which will give us 60 and 4. Okay. So this will give us, again, for the other input, okay, we can take 0, 0, 81, which will give us 81, and then 81 combined with 120 and 3, which will give us 204. Okay, and this essentially then gives us this output here, and the final part will be to map, where we take each of these tuples and we transform it. We transform it by dividing the sum by the count to give the final average here. Okay, so I think I'm pretty much out of time. Any questions? We can continue, finish the class on Wednesday. Any questions about this? I know there's like it's something I've seen in previous years that people struggle to understand, but hopefully with the examples, you understand it a bit more. Does it make sense? More or less? Okay, so you'll be using it in the lab on Wednesday anyway. So you'll see aggregate by key and these features in the lab. So yeah, so I guess if there's no questions or doubts or comments. It'd be good to keep going until have more time for the lab. Yep, I'm open to that, of course. I think it'd be good to have a vote. I think we're, in general, I've been doing hour-long classes since we started online. I obviously don't mind going a little bit longer. So we can do a vote and see. We can see what's more popular. If you prefer to do more in the class, to have more time for the lab, that's perfectly fine. What was I going to say? I do try to cut. I've tried to cut some of the content from the classes. Maybe there's more I could cut, but it's at a certain point it becomes difficult to get it below an hour, let's say, or some of the classes at least. So we can have a vote and see what people prefer. Yep. Okay. So if there's no questions or doubts or comments, for now, anyways, we'll continue on Wednesday. I don't think there's too much more to talk about. It's more the overall flow of Spark jobs. So I think maybe around 10 to 15 minutes, but I always say that and I take 20 or 25 minutes. In any case, see you on Wednesday. So.